Hello everyone, welcome back to De La Cruz engineering videos. So in this video, we'll be having sight distance on vertical summit curves. So we have a featured problem here to be solved in manual. And afterwards, we'll be comparing it to the formula derived in this specific kind of problem. Okay, so before we start, let's have a definition of a sight distance. A sight distance is a length of the roadway ahead visible to the driver. For purpose of design and operation, it is termed the stopping sight distance or the passing sight distance. So as you can see in this figure, we have here an approaching car, and on the other side of the road we have here any object. It can be a man. Okay, and this is the stopping sight distance, the required stopping sight distance. Okay, this should be the minimum. It is more conservative, or it is more safe. It is safer if we have here a longer than the required minimum stopping sight distance. Okay, so in this problem, we'll be designing the required length given the stopping sight distance. Okay, all right. So a vertical summit curve has tangent grades of 2.2% and negative 1.8%. The required stopping sight distance is 100 meters. Design the length of the curve. Okay, so we have here our figure. So in stopping sight distance, we have two cases. In this figure, S is lesser than the length of the curve. Okay. The other case, S is greater than the length of the curve. So we have no choice here. We need to assume either way, no? It's up to you what assumption you'll do first. So in this solution, I'll be assuming first that the S is lesser than L. Okay? So that in this case, the H1 and H2 will lie on the curve. Okay? Otherwise, when S is greater than L, H1 and H2 will not lie on the curve. It will lie on the tangent grades, or basically the straight road, inclined straight road. Okay? All right. So, by the way, H1 and H2, if it is not stated on the problem, we have here a design standard. Okay? So, commonly, on the reviewer books, if you try to search for it, we have the design standard for H. Okay? All right. So, design standards. So the design standard for H1, that is a 3.75 feet. Okay, and in this problem we have here in English unit, so we'll just take this one as 1.14. Okay, for H2 we have there 6 inches. Okay, and taking this one in 2 meters, this is we commonly take this one in 2 units, 0.15 meters. Okay, actually these standards here, this constant value here is an old standard, no? If you try to check the DPWH manual, the latest, no, the latest manual, we have there H1 as 1.08 meters and H2 as 0.6 meters, if I am not mistaken. Okay, but most of the reviewer books, they just use this old standard. Okay, 1.14 and 0.15. All right, anyway, if the problem specifies value of H1 and H2, then that should not be a problem. Okay, then in this specific problem we have here, we don't have given for H1 and H2, therefore we'll be using these standards, 1.14 and 0.15. Okay, now how can we solve the length of the curve? Okay, focus on this one. This is the side, the line of sight, and this is tangent to this curve, no? Basically, this will be our summit or the peak point of the road. So I'll just call this one as X and Y. Now, as you can see, that the stopping sight distance S is equals to X plus Y. So all we need to do here is to express X and Y to L. Okay? Now, how can we do it? So I'll just extend it to this one. Remember that we have the formula for this value here. That H, the vertical offset distance from PI to the curve. At this H, the formula for this is expressed to L. Afterwards, by square property of the parabola, then X can be expressed to H, which is H is expressed also to L. Okay? So to have that, all right, the H is equal to that is L over 8 multiplied by A. So I'll just have A here as the arithmetic sum of the grades. Okay? So in this case, A must be equal to G1 plus G2. Okay? So we'll just take the absolute value for the grades. If the grade is negative, then we can have this one as positive 1.8%. Okay, so solving for A is equal to 0.022 in decimal plus 0.018. That is 0.04. So some books here uses A as in percent. No? So if we use A as percent, we'll be using here 800. Okay? If we use A in decimal, this is L over 8 lang. Alright. Now, again, as I have said, S, by the way, we assume S is lesser than L in our first assumption. Okay? So, S is lesser than L. So, our main equation that would be S is equal to X plus Y. Now, we'll be expressing X and Y to L. That could be expressed by ratio and proportion. I mean by square property of the parabola, no? Now, by SPP, as you can see, we can have here X squared is to H1 is equal to H is to the, that is not H, that would be equal to L over 2 from the H to L over 2 to the point, endpoints over H. Okay, that is L over 2 or 0.5 of L squared is to H. Okay, similarly, we can also have Y squared. Remember for SPP, we squared the horizontal distances. If the parabola is concaving upward or downward. Okay, recall geometry. So we have here H2 is equal to, that would be the same to this. All right. Now, take note that H is expressed to L, which is L over 8 times A, and A is 0.004. So in this case, we'll be expressing X and Y to H or to L, no? That would become square root. Actually, we can just factor this out or bring that out, no? 0.5 of L square root of that is H1 over H, over this H. But this H is equal to L over 8 times A. And A is 0.004. So I'll just have this one as 0.04 over 8 multiplied, by the way, by that one. Okay? So this is the x expressed to L. Similarly, we can also have y is equal to, actually this is the same, no? To this one. But this is H2. Okay? Similar derivation for that. Okay, so you can simplify this further, but I will not do it here. Okay. Now, following this equation here, we can have S as 100 meters. S is equal to X plus Y. But take note, X is this. All right. And Y plus Y is this equation. Okay. So, you can go further for this if you want to simplify this. But actually, this can already be solved using our calculator. Okay. So, I'll just leave it to you if you want to derive the formula for this. The formula for this will be derived if we simplify this further. Anyway, so I'll just have this one as our syntax in MathCAD software. We want to find the L. I'll just assume L as any value for that, no? Using this software. So then we'll have L find L. Using your calculator, you can just do the shift solve. Okay. So by the way, H1 is 1.14. H2 is 0.15. Okay, so this is in meters, of course. Now, take note that we first assume that S is lesser than L. Now, as you can see, S is 100 meters. Take note, S is 100 meters. Now, this is actually greater than our L we calculated, which is 94.47. Okay? We got here 94.47. Therefore, our assumption here, we assume that S is lesser than L is wrong, no? So this is not okay. Okay? Therefore, the correct value for this, L should be greater than L. I mean, S is greater than L. Now, this value here is not acceptable. Okay? Because take note that H here and H1 and H2 fall on the curve. If S is greater than L, then this H1 and H2 will not fall on the curve. That will fall on the tangent grades. Okay? So, using H, now we have actual scenario, S should be greater than L. Okay? This will be our actual scenario. By the way, before we proceed to this solution, we have a formula for derived formula for this. If you want to memorize this one, when S is lesser than L, this is the formula for that. AS squared over 200 quantity square root of H1 plus square root of H2. If we try to use that one, L is equal to, by the way, if you use A here in percent, that would be 200 in this one. If you use A here as decimal, this would become 100. Okay, it's up to you what you'll be using. So I use A here in decimal. We have here 0.04. S is 100 squared divided by, that would become 2. Okay, 200 divided by 100. Quantity, square root of H1, we have here 1.14 plus square root of H2, we have there 0.15. This is quantity square. So that would be equal to 94.471. It gave us the same to this value there. But anyway, it is this is still not correct, no? Because actual S is greater than L. Okay? So, we'll be using the actual S is greater than L. So, why is it that this value of L is not acceptable? Okay. Now, focus on this figure. If this S is greater than L, then H1 and H2 is on the tangent line. Okay? Therefore, we do there the square property of the parabola. But in this case, since H1 and H2 is not on the curve, so we cannot use directly the square property of the parabola. Okay, I hope that is clear. So in this scenario, we can have here, S is equal to, as you can see, X. Our X here will be from this point of intersection of the horizontal line or the line of sight to the grade of tangent. Okay, similarly to this, the grade of tangent here and the horizontal line intersection. So S, as you can see, that would be X. By the way, from this point to this point, that should be L over 2, property of a parabola. The tangent grades will meet halfway, always in a parabola. Okay? S is equal to X plus Y plus L over 2. This would be our main equation if S is greater than L. S is equal to, we can have, rearrange that one, L over 2 plus X plus Y. Okay. Now, as you can see, that X here is equivalent to H1 over the grade. Okay? Remember that the grade is rise over run, H1 over X. Therefore, X can be expressed as H1 over G1. Okay? Therefore, simplifying this one, S would be equal to L over 2 plus X is equals to H1 over G1. And also Y is expressed to H2 over G2. Okay? So, take note for this, we take the absolute value of G2. Okay? Disregard the value of negative sign. But in this scenario, we cannot use directly G1 and G2 here, which is 2.2% and negative 1.8%. What will remain constant here is the actual value of the change in grade, that is the A, which we calculated, that is 0.022 plus 0.018, that is 0.004. Okay, this is the only constant. We need to differentiate S to G to the grades because we want to calculate the minimum required stopping sight distance. Okay? Here, the stopping sight distance is given. Therefore, we need to calculate the equivalent required length. Okay? We'll take this one as the minimum required stopping sight distance. Now, to do that, since we have three variables, I mean, this S is a variable. We do not know that yet. That is given, but we'll be minimizing this equation. G1, we take this one as a variable. G2, we take this one as a variable. Okay? L2 over 2, L over 2 is constant. H1 is constant. H2 is constant. Therefore, S, G1, and G2 are variable there. Okay? Remember, we cannot use directly 2.2% and 1.8% here. The constant for the grades would be their difference, I mean the angle between the tangents. This is actually the angle between the tangent grades. Okay? So differentiating this one to have the minimum length, that would be ds over the derivative of grades. Okay? Okay. By the way, let me just have this one. If A is equal to G1 plus G2, so I'll just have this one as prime. Okay? G1 prime and G2 prime. Because again, we'll not use here the actual grades given there. but instead we'll be just using the constant change in grades, which is A. That one. Okay? Therefore, this one here, that would be S is equal to, I'll just express one grades there to the other. So that would be, this one is A minus G2. Okay? Or I'll be just expressing this one to G1. Transpose G1 there. Let's have it prime, no? That's not the actual value of the given there. Okay. Now, differentiating these ones with respect to the grade, ds over dg must be equal to 0. Okay? To have it minimum or maximum. Okay. Derivative of L over 2, that is constant, that would be 0. Now, derivative of this one, that would become negative 1 or negative h1 over g1 squared. g1 prime, no? Squared. Okay? Derivative of this one, okay, we can use derivative for division, no? VDU plus UDV. So that is VDU plus UDV. We have here our V as A minus G1. So V A minus G1. Prime. Derivative of U. Our U here is H2. But H2 is constant. Then it would become 0. Okay. Minus UDV. U is H2. Okay. Derivative of our V, A minus G1, that would be negative 1 divided by the V squared. That would be A minus G1 prime square. Okay. So as you can see, simplifying this one, this will become, we'll be expressing H1 over G1 squared is equal to, this should be H2 over A minus G1 prime squared. These are both prime, no? Now, in this specific equation here, we'll just need to have expressed this G1. Actually, this is our prime. G1 and G2 prime to A. Okay? Now, as you can see, simplifying this one, we can have this as, okay? Diba, we can have this as G1 is equal to the square root, no? Or we can have A minus 1. A minus G1 prime times the square root of H1 over H2. Okay? So simplifying further, no? We need to express G1 to A with respect to H1 and H2. So we can have G1 prime is equal to, okay? How do we simplify this? A multiplied by the square root of H1 over H2 divided by 1 plus square root of, actually the same for this. Okay, just recall algebra. And also we have here a little calculus. Okay, so this is our G1. So you can simplify this further, but I will not do it here. Okay, so we have our G1 prime. And take note, we can also have our G2 prime expressed to A. Okay, remember that G2, I just have it here below. Take note that G2 is equal to A minus, this is G2 prime is equal to A minus G1 prime. Okay? But G1 prime is this equation. Okay. So this is how long you do if you do You do this if S is greater than L. This is for manual solution. Okay? Now, we have G1 prime. These are all constant, no? We can now substitute this value to this main equation. Okay? So I'll just have it here. That one. Okay. Now substituting the values there. G1 is this. G1 prime, I mean. G2 prime is this. Okay? So, by the way, we did not use our G1 and G2 in this problem because we need to what we call this, we need to differentiate this one, or we need to minimize or maximize the L. I mean the S. Okay? I hope that is clear. So this is how long you do it if you solve this manually. So here we can now find our L. I'll just have here as our given. Again, I'll just assume any value of L here. Then our S is 100 meters. H1 is 1.14. H2 is 0.15. Okay? 1.14, 0.15. Okay, just follow the values there. Okay. By the way, our A is 0.004. Also this one. Now, if you try to simplify this further, we can came up to a formula for this, no? But I'll just do it this way to have a lesser time in recording this video. So L is equal to find the L. Okay, now as you can see, S, which is 100 meters, is truly greater than L, that is 94, approximately 94.15 meters. So this is now our answer. This is the answer. All right. So using the formula, no? This is the formula actually for that one when S is greater than L. So let's try to evaluate that formula if this will give us the same answer to this using the manual approach. All right. Okay. Using that formula, we can have L is equal to twice of S, 100 meters, minus. So again, this is 200 if we take A as percent. So I'll just have this one as 2 because I take A as decimal. Square root of 1.14 plus the square root of 0.15 squared divided by 0.04. Okay, so taking the value that is the same, 94.148. 94.148. Okay, this is the answer. Okay, so this formula is derived if you try to simplify this further. Okay, that's why it is very advisable for this specific problem to just memorize this formula. This is how long, no? But if you are undergrad student, so it is highly suggested you know where did it came from. Okay, same as to this first assumption. Was that this one? Same as to this. Where did this came from? Just from here. Okay. So I hope you learned something on this video. So thank you for watching and see you on our next tutorials.